Hello everyone, I am G. Nirnaya Rao from Department of ECE. Today I am going to do a presentation on star and delta connection through phasor diagram. Three-phasor system from the backbone of modern electrical power generation and distribution. There are, they are preferred over single-phase systems because they provide constant power transfer, better efficiency, and enable the use of smaller and more economical machines. In a three-phase system, we have three alternating voltages, each displayed by 120 electrical degrees. This phase separation ensures that the total power delivered remains almost constant at all times, which is why industries and power networks rely on it. However, three-phase can be connected in two distinct ways. The star connection, also called the Y connection, and the delta connection, also known as the mesh connection. Understanding how these two configurations work, and especially how their voltages and current relate through phasor diagram, is essential for every electrical engineering student. By using phasor diagram, we can visually represent the phase difference between voltage and currents, making the relationship between line and phase quantities much clearer. Star connection concept and configuration. Let us begin with the star connection. In a star configuration, one end of each the three-phase winding is connected together at a single neutral point, while the other end are connected to the three-line conductor. So in simple terms, the three coils meet at one common point, the neutral. The voltages measured between each line and the neutral are called phase voltages. The voltages between any two lines are called line voltages. If we label three phases as A, B, and C, then we have phase voltages VAN, VBN, and VCN. If a balanced system, each phase voltage has the same magnitude but is separated from the others by 120 degrees. Line voltages, these are the voltages measured between any two line conductors. Key relationship. From the phasor diagram, it becomes visually clear why the line voltage's magnitude is balanced star connection. In a balanced star connection, it also shows that line currents are equal to phase currents because each phase winding is in series with its respective line. Phasor diagram for star connection. To understand this visually, let's draw the phasor diagram for the star connection. The line voltages are the difference between two phase voltages. When you plot these on the same diagram, the line voltage vectors from another set are root 3 times larger than the phase voltages and lead them by 30 degrees. Hence, the relationship are V line equal to root 3 into phase, whereas I line equal to I into phase, I of phase. This relationship is crucial and the phasor diagram makes it immediately visible. Let's take a quick example of star connection and application. Suppose each phase voltage is 230 volts, then the line voltage will be root 3 into 230, which is equal to 398 volts, which can be taken as approximately 400 volts. That's why in many distribution systems you will see 230 volts single phase and 400 volts three phase supplies. Star connections are typically used on the secondary side of transformers and in long distance power transmission because the neutral point allows two voltages line to line and line to neutral and support both single phase and three phase loads. Delta connection concept and configuration. Now let's move on to the delta connection. In this configuration, the end of each winding is connected to the start of the next from a closed triangular loop. Here, each side of the triangle represents a phase winding. The line terminals are taken from the corners of the triangle. In a delta connection, V line equal to V phase. I line equal to root 3 into 5 I phase. Unlike the star system, the neutral point does not exist in a delta configuration. This makes delta connection well suited for industrial motors and high current applications where neutral isn't required. A key characteristic of delta connection is that the line voltage is equal to the phase voltage. This is because the measuring points for the line voltage and directly across the phase winding on a phasor diagram. This means VL and VP phasors will have the same magnitude. The line current in a delta connection is the vector difference of the two phase currents flowing into or out of a junction due to 120 degrees phase shift. Let's now draw the phasor diagram of the delta connection. First, draw three phase voltage forming a closed triangle representing the three coil connected end to end. However, the lines correct are found by taking the vector sum of two phase currents meeting at each junction. The resulting line current phasors are root 3 times greater than the phase current and lag by 30 degrees. The graphical representation makes it much easier to understand how current divides and combines in delta systems. Something that's not immediately obvious from equation alone. By comparing star and delta connections, let's now summarize the key differences between two systems. Line voltage in star connection is root 3 times of phase voltage, whereas in delta connection is equal to the phase voltage. Line current in star connection equals to phase current, whereas in delta connection it is root 3 times of phase current. Neutral point exists in star connection but does not exist in delta connection. Applications of star connection are transmission, distribution, balancing loads. Applications of delta connection, motors, heavy industrial equipment. So depending on whether we need a neutral high voltage or high current, we can choose the suitable configuration. This is a step-by-step guide for introductory engineering. And the conclusion is phasor diagrams are an essential visualization tool in electrical engineering. They help us understand how voltage and current behave in star and delta connections, how they are related by factors of root 3. And that's it. Thank you.